Assalamualaikum and very good morning to Dr. Anahwa. Good morning and greeting to everyone. Today, I would like to present our project for the course Digital Signal Processing BERT 3373. The title of our presentation is Win-Win Filter, and for this presentation, I will focus specifically on the rectangular window. This presentation will cover the theory, characteristic, Melodiza is a real-life application of the rectangular window in digital signal processing. This slide shows the title of our project, Windowing Filter, for the course Digital Signal Processing. Windowing filters are very important in DSP because they allow us to design practical filters from either mathematical models. This project prepared by two group members, which is I am ZULFIKAR BUKHARI with match number B12341047 and my group partner is which is Muhammad Zamir bin Rafiz, match number B12341042. The objective of this project are listed on this slide. First, to demonstrate our understanding of windowing filter. Second, to show how the filters are designed and using MATLAB. And last but not least, to demonstrate the real-life application of the selected window. For this presentation is focused only for the rectangular window to clearly understand its behavior and limitation. Introduction. Digital signal processing relies heavily on a filter designed to analyze and manipulate signal. Ideally, filters are derived from the infinite impulse response. However, infinite signal cannot be implemented in a real system. Therefore, we use a technique called windowing, where the ideal impulse response is truncated into the infinite length using a window function. This method is commonly used in FIR filter design and spectral analysis to reduce leakage. Okay, this is one of the filter we use in windowing, which is a low-pass filter. Low-pass filter allows signal below to certain cut of frequency to pass, while attenuating high frequency. Low-pass filters are widely used in the noise reduction, audio processing, and sensor data analysis. In our project, we designed a low-pass filter that allows a 50 Hz signal to pass and suppress 200 Hz noise, which represent unwanted interference. Okay, this is a windowing filter we choose. For this project, we have chosen the rectangular window. This is the simplest window and is often used as a reference to compare with the other windowing technique. Understanding the rectangular window helps us to understanding why more advanced windows are needed. The rectangular window applies equal weighting to all samples within the observation interval. It abruptly captures the signal at the beginning and the end. Mathematically, the rectangular window has a value of 1 within the window length and 0 outside. Because there is no smoothing at the edge, this creates sharp discontinuities in the signal. In the frequency domain, the rectangular window has a narrow main lobe, which provides a good frequency resolution. However, it also presents high side lobes. These high side lobes cause spectral leakage, where energy from one frequency spread to another frequency. This leakage can distort frequency analysis, especially for non-periodic signal. Okay, this is advantage and disadvantage of rectangular window. The main advantage of rectangular window is simplicity. It's easy to implement, preserve signal amplitude, and provide good frequency resolution. However, it's a major disadvantage. It's severe spectral leakage due to abrupt truncation. Because of this, it is not suitable for the signal with closely phase frequency of high accuracy requirement. Okay, this is the whole MATLAB coding for the rectangular window. Okay, demonstrate rectangular window. Okay. Okay, we got firstly we got a setting setup. Okay, what we get in here? Okay, we we provide 100 kHz for the fs, which is sampling frequency. Second, we produce a time. Okay, time vector is 1 second, and we create signal which have a 50 Hz on one third signal, and 200 is noise, which is we put here sine to pi 50t and 0.5 sine to pi 200t. Okay, this is the defined rectangular window. We filter order we put a 15. Okay, window is a rectangular window function. This is the function of rectangular window. Okay, this is a figure 1. Figure 1, we show the rectangular window, which is filler width 1.5 and rectangular window at that function. Okay, this is the example. Okay, this is an example of rectangular window at that function. Okay, we can see it's just like a rectangular. It's a rectangular, okay? You don't like a sine wave or whatever. Second, if design FIR filter. Design a low pass filter cut off 100 Hz using the rectangular window. The cutoff is 100. The fs we put here is 1000 kHz. Okay. Okay, we reproduce the cutoff window here. And the figure will be here. Here is a big rectangular. Here, if I cut off window. Here. Okay, this example of a rectangular with low pass filter, which is the low pass filter is smoothly going down like this. Okay, this low pass filter going down, and this pass filter going down. Okay, firstly is a frequency response, which is a rectangular window. You can see that this like this. Okay, the magnitude is 0. It's slowing down to negative. Around 50, negative 50 dB. Okay, this is a phase. Okay, phase exactly like a frequency response. Okay, the low pass filter will work like this. It's going down. Okay, we continue the figure 3. Application filtering. This is a filtering. Output sini filter by the rectangular one input signal. Okay, the figure 3 we show the output after the filtering. Okay, this is a figure 3. Okay, this is an input noisy signal, and this is an output filter with the rectangular window after we filter with the rectangular. Okay, you can see here exactly have a distortion, and it's a sine wave. Okay, the maximum of this is around 1.3. This maximum almost 1. Okay, so basically this is the whole figure we of the rectangular window filtering. Okay, we got the basic rectangular filter. Second is the frequency response and phase after with the low pass filter, and this third is after noisy signal filter with rectangular window. Okay, next we Okay, real life application. Before filtering original noise signal, content replacing a raw unprocessed input such as audio capture by a microphone or data from communication reserve. Visual characteristic. Waveform is jagged and irregular. It consists of a desired or frequency signal, like 50 Hz, contaminating by unwanted high frequency noise. Cause is the cause is electrical interference, environment background noise, or a chain distortion. Status unusable because its signal quality is too poor for accurate analysis or reliable playback. Real application like processor data or process audio recording. Okay, this is after we filtering by rectangle window. Action alpha filter is applied using simple rectangle window. Visual characteristic, the high frequency noise is reduced and the distance sign where its shape is visible, however, it reverts slightly distortion remain. Okay, this is the slightly distortion remain. Okay, sometimes we cannot 100% uh smooth, cannot sometimes. Okay, state acceptable for the basic use, good for the system where speed is more important than perfection, and real application, basic FFT analyzer, simple vibration monitoring, and introductory DSP tools. Okay, that's all for me. I will give next to Zamir. Thank you from me.
Welcome and hi. I will continue for my part, which is the second windowing filter, which is Blackman-Harris window. The Blackman-Harris window of length n is defined as W of n equal to A sub of 0 minus A sub of 1 cos in bracket 2 pi n divided by n minus 1 plus A sub of 2 cos 4 pi n over n minus 1 and then minus A sub of 3 cos 6 pi n divided by n minus 1. This is a generalized cosine sum window. It uses a four-term summation to create a very smooth bell-shaped curve that tapers gently to zero. As we can see at the top here, this is the Blackman-Harris window. Okay, so for the Blackman-Harris window characteristic, the Blackman-Harris window has a very low side lobe level and excellent leakage separation in the frequency domain. However, this improvement comes at the expense of a wider main lobe, resulting in reduced frequency resolution. For the Blackman-Harris window advantages, the main advantage of the Blackman-Harris window is its very high lobe attenuation, making it highly effective for analyzing weak frequency component in the presence of strong signal and noise. However, for the disadvantage include poorer frequency resolution due to a wide main loop and reduced amplitude accuracy. It is also more computationally complex compared to simpler window such as the first window, which is the rectangular window. Now I will continue to the MATLAB part, which is to designing the Blackman-Harris window. So I will explain the code. For the first step, we need to set up the signal parameter, which is we set the fs, which is the sampling frequency, to 1000. For the time vector, we set to the 1 second duration. Uh, Next, to create a noisy signal, we use 50 Hz as our desired signal and also 200 Hz as for the noise component. Here, we set the 50 as our desired signal and 200 for the noise component. For the second part, which is to define Blackman-Harris window, we use the FI filter order n equal to 50, which is to for the Blackman-Harris window coefficient, we set the window equal to Blackman-Harris n plus 1 to define the Blackman-Harris window. Next, we need to plot the window shape, which is in the time domain for figure 1. So this is the for the figure 1. We set the stem, title, X label, and also grid and the axis for the figure 1. For the third part is for the FIR filter design. We set a normalized cutoff frequency to 100 Hz, which is here, the code. Cutoff is equal to 100. We divide it by fs divided 2, divided by 2. Next, to design the low-pass FI filter using a Blackman-Harris window. So this is the filter coefficient output for the Blackman-Harris window, which is the BBH, B underscore BH. Next, for the plot frequency response of the filter, this is for the figure 2. So we need to set the frequency and the title. For the fourth part is to apply filter to signal. So this is the code. So this is the output signal equal to filter and also the Blackman-Harris coefficient 1 and input signal. Next, we need to plot the input and output signal time domain, which is this is for the figure 3. So we set the subplot, plot, and also title for the figure 3. So let's run the code to see what we get. So here is the figure after running. I have 3 figure here, figure 2 and figure 3. For the figure 1 is the figure show the Blackman-Harris window in the time domain. We can see that the window start from 0, increase smoothly to the top to the maximum at the center, and decrease smoothly back to 0, as we can see here. The smooth tapering is important because it's reduce abrupt changes at the signal boundaries. As the result, spectral leakage in frequency domain is significantly reduced compared to the rectangular window. So next, for the figure 2, the figure show the frequency and also phase response of the FIR low filter designed using the magnetic response is flat below 100 Hz, which means the desired 50 Hz is still preserved. Frequency above the cutoff are highly attenuated. The phase response is quite linear, which confirms that the filter introduced minimal phase distortion. For the figure 3, in this figure, the top plot shows the input signal, which is consists of a 50 Hz desired signal mixed with 200 Hz noise. The waveform appear distorted due to presence of high frequency noise. After applying the Blackman-Harris window, we can see at the output signal become much smoother and closely resembles a clean sinusoidal waveform, which is show us that the high frequency noise has been successfully removed while maintaining the desired signal. So that's all for the MATLAB and designing Blackman-Harris window part. The real life application. Before filtering, which is the original noisy noise, as we can see up here, the noisy signal as the input. For the context, it is represent raw unprocessed input such as audio captured by a microphone or data from a communication receiver. For the visual characteristic, the waveform is quite jagged and irregular. It is consists of a desired low frequency signal, for example 50 Hz, contaminated by unwanted high frequency noise, for example 200 Hz. The cause is the electrical interference, environmental background noise, or also channel distortion. For the usable status is it is unusable because the signal quality is too poor for accurate analysis or reliable playback. For the reapplication, It is a raw sensor data and process audio recording. Then we continue for the Blackman-Harris window, real-time application after filtering. For the action, we use the same low-pass filter, but using the high-performance Blackman-Harris window. For the visual characteristic, the waveform is exceptionally smooth and clean. The distortion found in the rectangular version is virtually eliminated. For the status, it is high fidelity and it is essential for system where signality is critical. Real life application, Blackman Harris window is used in professional audio processing, medical device such as ECG and EEG, and also advanced radar system. So here we are. It is the comparison for the rectangular window and Blackman Harris window. For the window shape, it is flat, where the constant value is all one. For the Blackman Harris window, it is smooth, bell shaped, and curved. For the start and end behavior, rectangular window, abrupt start and stop, while the Blackman Harris window gradually rise and then fall. For the smoothing effect, rectangular window has no smoothing. For the Blackman Harris window, it has a very strong smoothing. For the spectral leakage, rectangular window has high, poor side lobe suppression, while the other is very low, which is excellent side lobe suppression. For the main loop width, for the main loop wide, it is for the rectangular window, it is narrow, which is we can say the good have the good resolution, while the Blackman Harris window has a wide but also lower resolution. For the side load level for rectangular window, it is high, but for the Blackman Harris window, it is very low. The signal distortion for rectangular window is more distortion in frequency domain, while Blackman Harris less distortion in frequency domain. Computational complexity for rectangular window, it is very simple, but for Blackman Harris window, it is more complex. For typical equation, for typical application, rectangular window used in quick analysis, time limited signal, and basic FFT, while the Blackman Harris window used in accurate spectrum analysis and for noise sensitive measurement. For example use is for rectangular window is simple signal truncation, while Blackman Harris window is audio, vibration, radar, and spectrum analysis. We continue for the last part, which is the conclusion. In design, practical digital filter requires windowing to turn an impossible and infinite mathematical equation into usable code. This is achieved by multiplying the ideal filter coefficient by a specific window shape. The rectangular windows acts like a shortcut. While this is simple and separate close frequency well like in radar, it creates ringing noise that distorts the signal. In contrast, the Blackman Harris window uses a smooth, complex curve to gentle taper the data. Although this requires more calculation, it is generally the better choice for real-world application like audio and medical monitoring because it effectively eliminates noise leakage, which is resulting in a much cleaner and more accurate output. So that's all from us. Thank you.